I think it's official. Welcome back, everyone. I hope you all had a really great break. It's always kind of weird coming back after a really long break, so I think we should just kind of pause right here and ask any questions at the moment that folks would like to discuss. Okay, well, we had a couple things happen over the break. Exam 2 has been graded. If you have any questions about that, don't hesitate to ask. Also, if we go to the main Moodle website, I posted some brief summary statistics. I think I forgot to do that. I should update that. But the exam 2 solutions are also available if you want to take a look at those as well. Also, for what we've got going on this week, assignment 7 is due this Wednesday. But if you need extra time getting through to that one, I would understand. And in this course, despite what it says in the syllabus, I am taking late work. So if there's an assignment way back or even assignment 7 that you just need more time with, take that time, complete the assignment, and I will accept them for credit. So assignment number 7 is dealing with one mean. It's where we finally have our full procedure where there's no logical loopholes and things going on. And the good news is chapter 18 just kind of extends right off of that. Here we're considering two different means simultaneously. So hypothesis testing, confidence intervals have the same kind of interpretations and typical setup. Only thing that's a little bit different is this stuff right here. You have to make some modifications. We'll see that as well as we get into chapter 19. Well, aside from where we're going at the moment, we'll also have our third exam, and this one's going to be from our upcoming Wednesday of the 27th. It'll be 2 weeks away. So still plenty of time on this one. And I'm trying to really work with this testing center in Pocatello to get everything lined up in time. That's been kind of a challenge. We should be all set up, and I'll be starting to post materials on this weekend on the coverage. I'm thinking it's probably going to be chapters 7, 18, 17, 18, and 19 is what fits the best. But we'll have a better idea once we get closer and closer to that week there. Well, any other questions, folks, about the announcements so far? Okay, well, here's where we're at so far in the extended view of the course. I mean, we're really just about done. If we look at this portion of the page, then we'll have a couple content weeks, another exam week. We'll do it just as we did before. So we'll have a Monday review, informal one, that kind of thing. We'll be mostly wrapping things up on this week. We'll come back on this one. This is the penultimate week, week number 15. Monday will be a typical day, but Wednesday is going to be all about review questions and those kinds of things. Very end of the class on Wednesday, we'll release the final exam. We'll just unhide it on Moodle, and it'll be considered assigned to be due on finals week, May 1st. So that's the plan of attack so far. Any questions or comments at all, folks, at the moment? Yeah. It's nastier, but I wouldn't say it's totally nasty. Kind of what's going to go on with the take-home exam is we're going to go from chapter to chapter, everything that we've covered, and just assign one question that might fit best with that chapter. So it's going to be scrambled. That's the hard thing about the final exam. It'll be up to us to decide what's the right method. What should we pick here based on how the data looks, what the question is being asked. And that's the major challenge with the actual final exam. So it'll be typical questions like you've all seen, but one big document that we have to kind of untangle to decide what to do with what data. And that's the reason we'll have a review. I'll have another document with the same kind of skills that we'll be practicing on that week as well. Other questions about that? Yeah, it'll be one of those take-home exams, kind of not like exam 2. It'll be written sort of like a glorified homework assignment in a certain sense. Other questions about that at the moment? Okay, well, that's where we're going so far. And we'll have some reminders about this stuff as we're getting closer and closer. But for the moment, the bigger things are assignment 7's coming due this Wednesday. And now we're moving on to assignment 8. This might be an aggressive due date, but we'll just see where we end up. April Fool's is a weird day to accept homework, I think. And this is where we left off right here. We did a bunch of probability theory up there in the notes that you can come back to look at if you like. It's more reviewing central limit theorem and seeing how things come together. But this is the major results right here. This is our brand new central limit theorem in a certain sense. And it tells us some things that we kind of already know. For example, in statistical inference, our goal is to estimate that. That's the unknown quantity. Well, mu1 is unknown and so is mu2. If we're comparing them, we'd say mu1 minus mu2 is unknown. So that's our major problem, but we do have an estimate right away. We'll say, if we need to estimate this quantity, we go right here. Let's say, however, x bar 1 minus x bar 2 is approximately equal to mu1 minus mu2. So once we calculate this data, summary statistics from it, then we have a reasonable idea of what this quantity is going to be. But we made lots of complaints about this before, and we should reiterate those complaints. This is useless, pointing to the approximation symbol. It's of no value to us unless we can explain what the error is in that approximation. So let's say right here, useless until we express the error. And how do we do that? We need this quantity up here. But same kind of problem. We don't know the value of sigma 1 squared. We don't know the value of sigma 2, so neither it's squared. Instead, we come down here and estimate with the statistics, S1 and S2. And now we have estimates upon estimates. This thing, standard error of x bar 1 minus x bar 2, its whole purpose is to estimate that. And we did it by estimating each of the parameter values with statistics from the data. And so we're going to be punished by this a lot whenever we make more and more estimates to make a procedure happen. It's the same kind of redo as the t-distribution. So that's what we're going on so far. And at the moment, this is the major new thing that's going to happen in chapter 18, a brand new standard error, which means it's going to be a brand new degrees of freedom. And I think I got rusty. Here's a chat I missed. Sorry about that. Oh, yes, Sydney, that will be used for the final exam. I think someone was helping with class see that text as well. So yeah, R will be used on the final exam. But I did want to reiterate, when it comes to R, even if you're working on a final exam, if you have a problem with R, it's not working as intended, just email me. We'll get it resolved one way or another. We're only thinking of it as a calculator, not a major objective of the course. But other questions so far? Okay, just in case you're curious, the way I've been trying to figure out a chat's coming through is this little thing right here. I'm not sure if you can see it on the actual Zoom client, but there's a little control bar right here. If you can't see it, let's put in a screenshot. It looks like that. I'm not sure if you can see this or not in the Zoom class. I usually put it down at the bar and it's supposed to hide and then pop up when a chat comes in. But apparently every time this thing updates, something new gets broken and it no longer hides. So if I'm missing your chat, maybe send it again, or anyone in class can wave at me, let me know I missed one, or anyone in Zoom as well, just type in and say, hey, there's a chat, and then never be considered rude. They're getting really hard to spot for some reason. Well, that's our new thing, the standard error. And when we went down, this is about where we ended class right before spring break. So that's why we're going over it again. That was a long break. This is the modification to our procedure so far. Our old confidence interval, I'll delete this in a moment. This is just for comparison. The old interval went x bar plus or minus a t star times standard error of x bar. And that standard error of x bar was nice. It was SCx bar is the sample standard deviation S divided by the square root of the sample size. But once we involve two distributions, it gets complicated. The new formula for this standard error is that quantity right there. The same thing we were pulling out of the central limit theorem. So that's not too bad of a modification. We're just using two different means to construct our confidence interval. Down here, if it's a test statistic, same idea. There's just going to be two means and the same standard error. And this is where it gets really, really interesting. Let's pause right here and mention one thing that this procedure is doing. This is not your ordinary two-sample t procedure. Depending on where you've learned statistics, sometimes people do an extra procedure before they even try two samples. They test for equal variance. That's not a bad process, except there are several equal variance tests. They are highly sensitive to problems with the data, non-symmetry and such. And it's a whole nother p-value or a whole nother confidence interval you have to take into account before you get to the main question, estimating mu1 minus mu2. So the procedure we're using that uses this degrees of freedom is the two sample test that does not assume equal variance. So we take that assumption of equal variance that is sometimes used and used legitimately. But for us, if we want a procedure that's going to work in the widest possible cases, have less issues with multiple p-values and multiple confidence intervals, this is the test that we're actually going to use. And it's a great test because if you use a two-sample procedure that requires equal variance, and you find that assumption is violated, you have to use this test either ways. And anytime you test for something like equal variance, there is always type 1 errors, type 2 errors issued with p-values. The major goal of statistics is to try to do as much as possible with a minimal number of procedures, less confidence intervals, less number of p-values altogether. And this does it for us. But the downside is we get a t-distribution, degrees of freedom given this way. It's not guaranteed to be an integer, but if your variances are close, it'd be close to taking both of your samples, adding them together, and just subtracting 2. It should be close to that number. This approximation for this degrees of freedom for the t-distribution are actually pretty accurate as long as this holds. Both sample sizes, let's start with both, have to be at 5 or larger. So if you get a sample with just 3 observations, probably we shouldn't even use this method. The method is not going to be guaranteed to be reliable at that stage. So the degrees of freedom has to be calculated for both a confidence interval and a hypothesis test. But one thing to note is that quantity is familiar. There's a slight shortcut here. S1 squared over N1, let me zoom in on this, plus S2 squared over N2 is just that quantity. Because it's not been square rooted, you could take this and to get this to power 2, raise that to power 4. You get just the standard error to the 4th power, and that's something you calculate anyways. So this saves a lot of time in getting the degrees of freedom. Really, you're just looking to the denominator to calculate it. The denominator does not look nice as well, but if you focus on just that part, that's half the denominator, and the only change to the other half is you change the subscripts. So there's a bunch of symmetry in that formula. Well, that's the formula altogether. And if we're doing a test, well, we'll just use the test statistic up here with the right degrees of freedom. And all this information is almost identical from before. One small change though. For testing, or for comparing two means, say 2 sample t procedures, I'm not sure why I scrolled up there, but the typical hypothesis test goes like this. We're almost always testing for the difference of the means to be 0. That's because the null hypothesis is a statement of no change. And the large question we often ask is there any difference between one population and another? So this is a statement of no, there isn't. And these are the statements of yes, there is, and here's how they could be different. I think this is highlight worthy as well. This is the next thing that's a little bit different. You can essentially assume for this entire course, there'll be a 0 there. You can modify the procedure and put something else, but those are less standard procedures. Well, any questions at all, folks, with looking at the overall methods? Okay, well, first thing we should do with all this fine, shiny new formulas is we'll try it out right away. So let me not delete the procedure. I'm gonna fix that. Oh, geez. Haven't used this keyboard in a while. Forget where the home row is. Okay, so here's our next example. There's a really quick edit here. I forgot the word brain, so that has to be right here for it to read right. Sorry for that omission. But here's what's going on in this study. It's older data of 1984, and it says in a pharmacological study, researchers measured the concentration of the brain chemical dopamine in 6 rats exposed to toluene and 6 control rats. This study was in the 80s, so I think they were looking at toluene as some kind of thing in aerosols that people were abusing and getting hurt by. So I think that was the purpose of this study. They say next, the summary statistics for concentrations of dopamine in nanograms per gram in the straight chain region of the brain are provided in the table below. And this is the source of the data. If you'd like to take another look at it. All we have here is summary data. And so this is a pretty typical question for an exam setting, say exam 3, something about like this. It gave us a lot of data, this time in a table. And probably before we get started, we might want to start coding things up and describing them. So for example, there is a treatment group in this experiment where all the rats got toluene with a sample mean, sample standard deviation. Not a bad idea to just leave it in the table, but if it helps, you could also just rewrite it into your own format. It's referring to a sample mean here, so we could say X bar. We could call it X bar 1 or X bar 2. If you decide to call it X bar T, feels more abstract unless you're just reminding yourself you're talking about the treatment group, X bar. I'll leave that all up to you. If you like X bar 1 versus X bar 2, just make sure 1 and 2 are well corresponded throughout the whole problem. Or you can just be more descriptive and give it symbols like that. So X bar T is going to be 2578.0 now grams per gram. And for the sample standard deviation, we'll call it ST for the treatment group, the toluene group. This one is 565.19 nanograms per gram. Then let's go over to the control data and just rewrite this into our own format as well. So X bar, we can go for C for control is 1880.4. And for the sample standard deviation, SC 411.84. Well, we've got it, folks. I mean, it's fine in the table, but sometimes this does help out, just writing it in the language or the format that you're about to use in the whole problem. They ask us the question, is there evidence that exposure to toluene causes an increase in the dopamine levels in rats? Well, looking at the sample mean, I'd say, yeah, probably, right? There's a huge increase, but the standard deviations are large as well, so maybe it's not as clear and cut and dry on this. And even if we were to say yes, doing this whole procedure is now going to give us an estimate between the two population means. So we'll have even more information after completing this process. But maybe one other thing to put down, the sample sizes are also important, and they can fluctuate on these. The most powerful studies will have a balanced sample sizes. Same number used for toluene, same number for control. That's not always a guarantee, and it's not always reasonable. Sometimes that's really hard to do in a study. But they said somewhere here, there were 6 rats exposed to toluene and 6 control rats. So we can say NT, and for the sample size, T for toluene is 6. And over here, NC, 6 as well. So that's our 6 variables all put down. Now we're ready to get started. Any questions or comments so far, folks, with the start of this one? Okay. Well, all these problems pretty much go the same kind of way. This time we want unknown parameters, so the new thing is it's plural. And usually this is referring to just our means, mu1, mu2, or mu-t and mu-c. So for this one, we can say let mu-t and mu-c denote the population mean. Now at this stage, I said mean, and I used mu value symbols only because our data is absolutely numeric, quantitative looking. We have 2 different means we're comparing against. But when we say population mean, we have to say mean of what specifically? So looking back at the data had this as a unit, was concentration of dopamine. So we'll say population mean, dopamine, concentration, specifically in the striatum region of the brain. I feel like if we pick up this part of the context, we've pulled in a lot of information already. We don't have to write out the whole problem. So this is all about dopamine. That's the values that are being recorded. I have 2 parameters here. We don't necessarily want to write 2 sentences. So here's a wonderful grammatical device. So that will be the mean dopamine concentration for rats in the toluene. I'm not sure if I'm even pronouncing that right, but let's keep on going with it. Toluene or toluene, that might be a little bit more accurate. Group and control group. respectively. So that word respectively is wonderful because now it's saying the moment UT came first, we was referring to the tolling group. And the moment UC came second is referring to the control group. And now we have a huge statement in one sentence. Saves a lot of time in an exam setting. Any questions, folks, with writing down those parameters? Okay, let me just highlight this in blue just to convey that's what we were looking for. So our conclusion is going to be based upon whatever we wrote down here, just as before. At this stage, this is the reason why we need a calculator for our upcoming third exam. We need a standard error. But when it says difference in sample means, this is the standard error we're calculating. SE of x bar 1 minus x bar 2. To do that, we need a central limit theorem. We go to the standard deviation portion of it and write out this thing. Everywhere there was a sigma, we put in S, the sample data. I already made a mistake here. I called it x bar 1 minus x bar 2, just because I'm used to 1s and 2s, but that should have been T and C. I have to keep that consistent for that to be a good strategy, so let me come back here. So the sample mean for the tolling group and the sample mean for the control group. There we go. Formula goes ST squared divide by NT plus SC squared divide by NC. 1s and 2s are nice, but it's good to be descriptive sometimes. From here on out, it's just plug and chug. Look up all of our values. For ST, it's 565, sensing the need of a longer square root here. 565.19 squared, and divide by 6. Then add to that, from this portion of the formula, we go over here for 11.84. Square that, divide by 6, and just get a value out. Easy to make a mistake on this, but if this is on your paper in an exam setting, that's a massive amount of partial credit. Next thing you do is grab your favorite calculator. Our studio should do just fine for this kind of work. And carefully input all that stuff. I'll try to get it in as one line, so SQRT for the square root. Then on the inside, we can just go top, bottom, left to right. Should be not too bad, actually. So 565.19 squared divided by 6, then plus, and over here 411.84 squared divided by 6. And that's finally our standard error. I'll keep all the 4 decimal places of accuracy, but does that look all right to folks so far? Awesome, so let's grab that, 285.4972. So now we have the standard error. The next thing which is fun is the degrees of freedom. And keep in mind on the third exam, just like the other exams, even the take-home exam, as silly as it was, there are going to be notes provided. I'll try to get those notes posted early so you'll know what to memorize and such. But I will give the formula for the degrees of freedom. I think that one is kind of nasty not to give a formula on. I have a cheat sheet over here in case I forget. It goes like this. Using the shortcut, I'm going to take standard error of the difference in the means, x bar t minus x bar c, and just raise that to the 4th power. So now we don't have to worry about recalculating the same kind of stuff right here. And I didn't make that well centered, but let's now go down below. The rest of it's going to involve first a fraction with the sample size reduced by 1. So using the first group, we'd go in like this. Then we take the standard deviation, ST, square it, and divide by the sample size, and then square that. So that's our format. Then if we've got that down, let me check my cheat sheet here. I think we're looking good. Then just recopy that format and convert your subscripts. This will be 1 over NC minus 1, SC squared divided by NC, quantity squared. So that's what it should look like as a formula. Now we've got to plug everything in. So first, the numerator, it's from this quantity, from the prior step, it'll be a 285.4972 to the power of 4. That just looks weird. Let's fix that. And then finally down below, let's see here. These are nice because they're the sample size at 6. So we'll have 1/5 in this location. From here, ST, we have 565.19, and we have to recall to square that as well, and divide by the full sample size, which is 6. Then square that result. It's always good to double check this stuff. There's a lot of things flying here and around. Does that look all right, folks, with that first term? Okay, well, let's keep on going. So plus, now we should be looking to over here for this next portion. Just like before, we'll have 1/5, sample size reduced by 1. Then take the 411.84, square it, divide by the full sample size of 6 for that group, square that, and we should have our degrees of freedom. Now, before we get too far, notice that the standard deviations, they are a little bit different. And if you use an equal variance test on this, it'd be a lot of work because it's summary data, but you could, that may or may not pass. But we're not worried about that. We're going to allow the variances to be different. However, our combined sample size is 12. If we thought we had perfect variances, perfectly equal variances, degrees of freedom should be right around 10. So we'll see how this modifies based off maybe the standard deviations really are different on this problem. Well, either case, it's back to the calculator, and this time we'll be really careful putting this in. Starting with the numerator, just go 285.4972 power 4, then divide by, we need another parenthesis around everything we see here, so that'll be our overall parenthesis. For the 5th times, new parenthesis for this one, 565.19 squared, divide by 6. Now I'm at that stage, power 2. And let's take another look at that. Order of operations can be funky. For using RStudio, you'll need to put in the times symbol right here. I think order of operations would be correct as it's written. We'll see how close we get. Then for the next one, we'll do it all over again. 5th times for 11.84 squared, divide by 6 squared. And that's our degrees of freedom. I recognize that number from this morning, so I think we've got it right. But how's that looking for folks? Are you getting about the same thing? About 9.14? Awesome. Let's take that. I'll take all of the precision they gave us, 9.14195. And not doing good with memorizing digits again. Hey, not too bad, 9.5. So that's our degrees of freedom. And because it's below 10, yeah, that is an indication probably the variances are unequal. And this is the modification we're going to make in order to get a most accurate confidence interval. What we mean by as most accurate as possible is this statement right here. If we do everything just right, we'll be correct when we say with 95% confidence. It's that statement we're trying to get accuracy on. Well, that's the worst part about it, the degrees of freedom. The rest of it is just typical formulas. For example, to get the critical number T star, exactly the same as you would have done it in chapter 17. So this is a good review of that. So we'll say T star. I think I want that whole thing to be green, not too sure. Let's just leave it as is. But T star is going to be equal to negative. I'm forcing it to come out as positive, so I'll throw a negative sign in. We're using the quantile function for the t distribution, so it's negative qt. Then after we have this, take the confidence level, and standard trick is to go 1 minus 0.95, divide by 2. So now we have area in just one single tail. Next thing we pull in is this number that got cut off a little bit. It requires the degrees of freedom, so 9.14195. You could set lower dot tail equal to false on this, but if you put in a negative sign, you wouldn't have to. You're going to get the positive value. So only things we had to put in is whatever the confidence is, convert to a decimal and just plug that in. And however the degrees of freedom came out, just plug that in there as well. This is the portion of part D on exam 3, where I would give you the T-star value, but for homework and the final exam, this will be a computation we would need. So let's test out that portion there. We'll go negative QT, 1 minus 0.95 divided by 2. I mean, that's not a hard computation, but the confidence is different. You don't really have to think about it. You'll always be really accurate if you take those extra steps there. Then 9.14195. And that's our critical number T star. It's at 2.2568. Now, if we didn't do anything special, if we try to do this with, say, the normal distribution, at 95% confidence, this would have been a 1.9600. So the extra or the higher number here is telling us our interval is going to be a little bit wider, and it should be because this is a huge estimate right here as well. It wasn't exactly the t distribution, and the degrees of freedom have been approximated as well. And so right here, this is our punishment for making approximations upon approximations. We get a pretty large critical number right there. But its purpose is, once again, to give accuracy right here when we say we have a certain amount of confidence. Any questions, folks, to get to part D? Okay, we're definitely cruising through this, so let's see what's going on next. For a 95% confidence interval for the difference in the population means, this is the format it would take. I usually start with a parenthesis because I like to associate the first two things together, even though algebraically you could just drop the parentheses. It'll be x bar t minus x bar c, add or subtract the critical number t star, and then multiply that by the standard error of x bar t minus x bar c. So that's our entire interval. All we need to do is plug in the information we have. Some of it's up here, so let me do a quick screenshot. So plugging all that in, we've got going in order as well. That's one thing that's easy to get a mistake on here. If you started with the treatment group, whether you call it X bar 1 or X bar 2, you have to be really consistent in how we plug these in. A switch right here is going to give us a weird result. So first, for the tolling group, it's 2578. Then for the control group, it was 1880.4. And subtract for T star, we've got it right here, 2.2568. And that will multiply the standard error, which is, let's scroll up for a bit, this quantity right here from part B, 285.4972. It's a lot of work to do all this, but it's valuable work in a certain sense. When you look at a statistical study, you don't always have access to the actual raw data. Even if you email the authors of that study really nicely, they may not give it to you. There might be reasons for that. It might be confidential data for some number of reasons. But if you have the table of the summary statistics, you can still do the full procedure in this kind of way. Also, good practice for just knowing how it works and for the upcoming exams. Is our purpose we're spending all this time going through it by hand. Well, any questions, folks, with the format right here? Okay, all that's left to do is just crank it out. So let's go grab your favorite calculator and put this in really carefully once again. So I can get these windows working. Okay, so left to right, it's 2578 minus 180.4. Then minus, using the lower sign first, 2.2568 times 285.4972. And that'll be our lower bound. So our first number, I guess we can round to a more reasonable amount. Let's go for 53.3 is our lower bound. And this was in nanograms of dopamine per gram of something, stratum region of the brain material, I guess. This is less than something. And right here, this is finally pretty new. Remember, there was two means altogether. They were mu t and mu c. And because we started with x bar t, we must put in mu t right here, going in the same corresponding order. Minus mu c is less than, then just do it all over again. Find the way to get to your last output in your calculator. For RStudio, it's up arrow. And honestly, this is the reason I put parentheses right here. I've made a mistake where I changed that sign, and that's not the right one to change. It's always a minus between the means. You want to change that sign to a positive. Really, the only true value putting the parentheses there, just to group things in the right format. So that goes to a watt, that's 1341.9. Nanograms of dopamine per gram of that brain region. Sounds kind of morbid when you say it like that, but that's what they did. Any questions at all, folks, with the confidence interval achieved there? Awesome. Let me take this. Let's just park it down here in case we need it. And I think we need a little bit more space. There's nothing wrong with the interval as written, but it does have one side effect that's a little bit hard to work around. And part F, if you give a practical interpretation to what you see right here, reading left to right or going from the middle, left and right, it's a pretty confusing statement because we have two populations being conflated into one overall interval. So sometimes it's a good idea to change this up just a little bit. Let's take some extra work on this. The study is all about the treatment group, the rats that were exposed to the toluene. Let's we'll isolate this one. Isolate since it's the treatment. And it makes sense if the study is about toluene being inhaled, we should be talking about that specifically. So let's add mu sub c to all three sides of this interval, and we'll get mu c plus 53.3 nanograms per gram is less than mu t, which is less than mu c plus 1341.9 nanograms per gram. Now with the treatment mean right in the middle, it's not so bad to interpret this. It usually go kind of in phases. You would mention this is between this quantity to this quantity larger than those values, whatever they are. Let's write it all out and see how it goes. It is tricky because there's more than one population going, but chapter 17 was our practice to get to this stage pretty much. Let's see, let's scroll to about this portion where we have the interval and our definitions down here in case we need them. Our interpretation could go like this. We have 95% confidence that we'll go here and just say whatever that happened to be. So down below, UT was the mean dopamine concentration for rats in the toluene, such a weird word, group. So I've mentioned this right here. Then we come over here and just mention these numbers, including the sign. We can say is from 53.3 nanograms per gram larger to up to this amount, 1341.9 nanograms per gram larger. Then, finally, we mention this portion, the mean dopamine concentration in the control group. Okay, let's take a look at that statement and see how we feel about it. We were just looking at the interval with none of these decorations on it. I'd probably say the mean of the toluene group is 53.3 higher up to 1341.9 higher than the mean of the control group. And that's pretty much what we said right here. So it looks like the toluene, on average, always had a higher dopamine concentration in that brain region than the control group did. Well, any questions about that interpretation there, folks? Okay, so I would say you can give an interpretation right here, but it has to read right, and grammatically that can turn into a really, really long, drawn-out sentence, run-on sentence, I guess is what the grammar people would call it. Sometimes if this works better for you, I think this is a clear way to write it out. But there's no points for style, so as long as I can read it and understand what you're saying, then you'll always get full credit. I would encourage, this is easier to interpret, at least for most people, not necessarily everyone. Well, let's get rid of that. There's also a follow-up question. I mean, this was the overall question of the study. They may have done this as a hypothesis test in the confidence interval afterwards. They ask us the question, does this study provide significant statistical evidence that exposure to toluene causes an increase in the dopamine levels in rats? Well, how do folks feel about that one? Would you all say, yay, we do have evidence of an increase, or no, we do not have that evidence? Some folks in class say, looks like we do have evidence. How about in Zoom? Does it look like we would have that evidence or not have it? Got some thumbs up. That's a great way to respond. Thanks, Olivia. And I agree with folks. This is good in that question. If it looked like this, and I'll fix this in just a moment, if this was like, say, negative 273, or just a negative sign right here, with a negative sign right here, we would have said, no, we don't have that evidence, because then there's a possibility that mu t takes on negative values. It would actually go below the control group. In fact, that was positive, and positive here is the only reason we do have significant statistical evidence of an increase. But notice, that wasn't by much. If that turns to 0 or goes negative, we would have said no right away in this kind of problem. Here we can say yes, because all values in the confidence interval are positive. Didn't have to be a big response on this one. Really, it's these kinds of things where we're giving a practical interpretation using a context, and we have to be pretty specific on how we write it out. But if it's just a kind of a yes/no question, then a yes or a no would have sufficed. I think I should have put explain here if it was a real exam question. Well, we did, folks. That's the full procedure for comparing two means. And there's loads and loads of studies now on the table that's a typical procedure we have. We're just analyzing one mean on its own. That's still interesting, but these are the kinds of studies that scientists really seem to like to look at. Multiple means, not just two, but potentially many groups. Well, that's how the confidence intervals go. The next one, we're going to take a look at how a hypothesis test should run. But before we do that, there's one thing we didn't hit on. If we're going to do this for, say, real data, like this one right here, it looks like it's important data already, then we ought to check the conditions on this kind of thing. If it's just a summary data, there's not too much we can do on condition checking. And so for example 4, if it's a complete analysis, there's almost an assumption that we'll look into conditions some way, somehow. So let's take a look at those. I highlighted some things that are new here, and these are a bit of a surprise. The Chapter 17 robustness conditions are actually a little bit more punishing when you have just one population. But it turns out if you're dealing with two populations, and the larger question are they the same or are they different, then we have more robustness on this procedure than we did for the old one. And if your distributions are not symmetric, that's a plus. If they're not symmetric with similar shapes, then that's also helpful for us. Having non-symmetric data, that was always harmful in Chapter 17. It's just less harmful this time. because we're looking at two populations, even if they have, say, two shapes that are skewed, but in the same directions, that's not going to be very harmful for us. This is a still helpful procedure. But watch out for this right here. Before you even get started using this two sample procedure, there must be a minimum sample size in both groups of at least 5. We hope it's larger, but that's the bare minimum to get started. So that's the first thing that happens with the procedures. And just like before, there's some things that we really can't address directly. We would have to be the people who designed the study. We were there present from the start to the end. And this is one of them. From our small window of looking at essentially an abstract of a real study, we don't really have the tools to assess if we have two simple random samples, but we'll still look for it to see if that's what is going on in the problem. The samples should be independent in the sense of this right here. Let's park the statements right here. This is actually more important than it looks, so let's see how we can make that just pop out. There we go. Is that still readable to folks with red on black? Definitely deserves good emphasis because this is where it's easy to make a mistake here if we're not checking it carefully. We don't have to write much, but we have to look. And here's how we can tell if data are independent. Look at these right here. These are 20 children that were considered typical children, and another 20 children who are considered schizophrenic. And there's no possible way that this row refers to one person any longer. They're totally different people. These data look independent. If you go to a different study, say somewhere here in chapter 17, we have just as tricky of a problem for a different reason. These data were dependent. And the only reason for that is the patients in this column were the same as the patients used in this column. The patient ID is here to just clarify that patient was used twice. This was his baseline levels, and these were the levels after the person was about to get surgery. That's what dependent data would always look like. And I would always have to clarify by adding a new identifier column to tell that it's really independent data we're looking at. But this is really dependent data that we're looking at. One value here depends on the other. So that's the way we can tell if we have independent or not, just by looking at the format of the data set as well. And any additional context will help a lot. So we'll carefully check some of these conditions, but for this, we will briefly discuss. Next, here's where we'll very carefully check. We'll also support our conclusions by including graphics as well, typically histograms, box plots if we decide it will be helpful. So we'll say carefully check and include supporting graphics. So the other thing our author does is, once we go to this procedure where we have two samples, all of the robustness conditions that you're seeing right here are pretty much the same as these robustness conditions from chapter 17. So it required if the sample size was less than 15, the data needs to look nice, no severe skew, no outliers. At least 15, we're okay unless we have strong amount of skew, and so on. But if you take all of these, go back here, and instead of saying N1, just your combined sample size is what goes in. So if your combined sample size is less than 16, the T procedures can be used if we have close to normal data. And if the data are skewed or outliers are present, we cannot use that T distribution or the T procedure. In other words, the only thing different here is this, the sum of the sample sizes. If it's a larger sum of sample sizes, you're at least 16. The thing we're looking for is strong skewness right here. That's enough to cause a big problem. But keep in mind, if they're both non-symmetric and they're both skewed in the same direction, this is actually a plus for us. This helps us with robustness. If your combined sample size is on the large end, then the only thing that's a real showstopper is severe amounts of skew or a hugely influential outlier and that kind of thing. So all we're going to do is combine our sample sizes and reuse the exact same robustness conditions that we saw from chapter 17. Any questions about those so far, folks? Okay, I notice my brackets are a little bit off here. Let me see if I can move this over. I want this to be the portion where we say, carefully check and support with graphics. And this portion right here, this is the one that you can skip outright if you want to. I mean, you should definitely read it, maybe once or twice. It says both population means mu1, mu2 from the first and second population are unknown. But we know that ought to be the case if we're estimating mu1, mu2 through a confidence interval or by a hypothesis test. That's the assumption already. And like before, sigma 1, sigma 2 are unknown, but you never have to really bring this up. The reason being is we are essentially assuming all of our parameters are unknown the moment we're doing statistical inference in most situations. So let's just put a note here, not required to comment. Essentially, you're using this procedure because you fit into this scenario in the first place. So that's what robustness looks like. And now let's give it a try for our new problem down below here. Well, any questions at the moment, folks, before we delve into these data? Okay, these are pretty interesting data, and there's a lot going on with this. This one is coming from psychology, and those are always very, very interesting experiments, I would say. It says here, the thematic apperception test. Never knew what that was until I read this problem. I'll refer to it as the TAT, for thematic apperception test. And what it does is presents subjects with ambiguous pictures and asks them to tell a story about them. So you can imagine you are being given this test, someone just shows you a weird picture and just tell a story based off of it. Weird test. They say next, let's break this up a little bit. There's a lot going on here. These stories can be scored in several ways. It just depends on what the study is really about. In this study by these folks, they asked mothers of 20 normal and 20 schizophrenic children. From right here, we know we have independent data just from that statement. The children were reused in the second phase of the study to complete the TAT and scored for the number of stories out of 10 that exhibited a positive parent-child relationship. They had to be very specific what they meant by that, but that's what the TAT score is going to mean in this case. Now, looking at the data, it looks like there are higher values for the normal children. When they took the TAT test, they had higher scores on, let's read that again, positive parent-child relationship. So this child is probably really happy. This child is upset, you can almost imagine. But it's not necessarily saying all of these children hate their parents. They have a disorder. They might have just been thinking about other things. It might have been a wonderful story they told, but it had nothing to do with parent and children. So they scored lower, it looks like. But that's the question. Did they score lower really on average? Is there a difference between this population and this population is now the larger question. But let's add something to the notes here, because if you come back to these problems, like say, this one right here is a very confusing problem, especially we're looking at a whole lot of problems with the final exam. This was the explanation of why we used the paired one sample t-test. And now for these data, let's go over here and say 20 children. This is a kind of a control, but I don't think controlled treatment is necessarily the right language. This wasn't a controlled experimental design. You can't assign a treatment of of schizophrenic, in other words. So this was 20 children as well. Let's say 20 different children. So that means we're dealing with a quantitative variable, but there are two populations here. Really, there is one quantitative variable. That's the TAT score. There's 40 TAT scores, so there is obviously another variable going on. There is also one categorical variable. With subcategories normal, and I'll just abbreviate that to skits. So this implies already use the two sample t-test. If you have one quantitative variable, one categorical variable with specifically two subcategories, this is the time we would use that test right here. If this categorical variable had three categories, maybe normal children, schizophrenic children, maybe a third condition we were looking into, we couldn't use this at all. We would have to use the analysis of variance procedure, the so-called ANOVA. So this is a nice test in that we don't have to get so fancy with ANOVA, and we can still get really, really powerful conclusions out of this. So sometimes with these problems, the explanation of why we're using the two sample procedure is almost more important than what we're about to do down below, because that's the hard thing with statistics. If data is just thrown at you, telling what to do with that data is not always easy. But we'll start to pay more and more attention to that as we add more and more procedures onto the table. Well, any questions at all, folks, with looking at the data and deciding on the right way to go with it? Okay, from here on out, it's all kind of the same sort of stuff we've been doing in chapter 14. Let's go down the line. We're going to completely analyze this data. Watch out for this on the homework, though. If it's asking for a hypothesis test, you might be asked to redo the problem for credit if you gave a confidence interval. And also watch out, it didn't give a level of significance. That's going to be up to us on this problem. So decide on what would be worse, a type 1 error, type 2 error. And if you have a level of significance you'd like to throw out, I'd be happy to take it. First thing we're going to do is just state the question that's implied by all these data. It seems to have a lot to do with the positive parent-child relationship through the TAT test. And we have normal children, schizophrenic children. Any volunteers for an overall question that we could put down here? Trying to see if there's something I could copy paste. It's always nice if there's a question mark. That's the first thing you want to look towards if there is one. How about for something generic? This would be something that's not too crazy, but it's a really just fast statement. It could go along the lines of this. Is there a difference in the TAT, the Automatic Apperception Test, or positive parent-child relationships, or however they define that? That's always a mysterious statement. For ordinary children and schizophrenic children. And if you put a period here, I would say that's okay, but it would be a little bit dangerous down the line, especially when we're giving a conclusion. There's one thing that's definitely missing here to make it feel just about right. Anyone see what's missing from this whole statement? It's pretty much that, absolutely. Again, not a big deal if you didn't say it here. I wouldn't be that picky. But it becomes a big deal over here because we're not saying there's a difference between any of the individuals in the respective populations. We're saying just that their overall averages within the two different populations, we can find a difference or didn't find a difference. So we should, just for best practice, say right here, on average. Or you could say with respect to the mean, if you want to use the word mean instead. Okay, so we've got that down. Next thing that's not as bad is we need the parameters Then after we define them, we have to define the hypotheses. So we'll start by writing down one overall statement. We'll define two parameters at once. Looking at the data, we could call this mu n and mu s. Or if you like, let's go with mu1, mu2, just because that's allowed as well. Let's take that second approach. So I'll think of this one as population 1. This one will be population 2. And I'll try to keep these consistent. So mu1 is now referring to the ordinary or normal children. I think ordinary children is better. If I say normal children, we might be thinking they came from a normal distribution magically. So let's go with ordinary children, same meaning. Let mu1, comma, mu2 denote the mean, or you could say average, score on the TAT for positive parent-child relationships. Then we have to say the populations. For mu1, we'll say for ordinary children. And for mu2, we'll think of the schizophrenic children. Then to make this fully grammatical and sensible, we'll just say respectively. And now we have a one-to-one correspondence between mu1, mu2, normal and schizophrenic. We've got that down. Next thing we need is a null hypothesis, an alternative hypothesis, HA. But the null hypothesis, like we said before, is nice in this kind of setting. The null hypothesis is a statement that there is no effect going on in the two populations. And that would mean the score for the ordinary children subtracted from the score of the schizophrenic children is 0. There's literally no difference in the population, is what we're saying, the moment we put down is 0. For the alternative hypothesis, well, we'll use a 0 as well. We'll also use mu1 minus mu2. And now we're back to the same kind of issue. The thing that goes in the middle here is either going to be not equals if this is a two-tailed test. If we feel like it should be a left-tailed test, we'll use a less than sign. If we feel like it should be a right-tailed test, we should use the greater than sign. But we should never base it on this. The data is irrelevant when it comes to which test we're selecting. In fact, if the researchers did this correctly, they would have stated everything, the parameters they intend to analyze, the hypotheses they intend to test, before they even saw the data. So just because the average looks higher here, doesn't mean it's going to be a right-tailed test necessarily. You have to dig through what they told us. They told us about the thematic perception test. They told us how they scored it, but there was no statement of test for one direction or another. This one is altogether a two-tailed test until we have the extra push from the right up that directs us to a less than or a greater than. So for this problem, it must be two-tailed. Does that make sense to folks on this one? To me, that's really tricky in a statistics class because we see the data. That's unnatural. That's not how statistics is typically done. You see this before you even look at the data. And all this comes from your research intentions, what you think you'll see, what you intend to collect, what you intend to test. And so just as a reminder, not equals is always the default. So now, after all that, we're setting these hypotheses only because it said use a hypothesis test. That means a confidence level is totally irrelevant at the moment. What is relevant is a level of significance. We will test these at alpha equals level of significance. So now we need to decide on our own, and this is what they would have done before collecting the data as well. What is an appropriate value for alpha? I'll leave this one entirely up to the class. Any volunteers for what we ought to select here? Anyone over Zoom have a favorite significance level that seems to fit? Look like you almost have one on the tip of your tongue. Oh, awesome. Thanks for spotting that. We've got a few of them. We'll go for the first one we see. How about a 0.05? You know what? Why not? Let's go for a 0.05 on this one. Sorry, Zachary, we'll go with Olivia just because she beat you just a little bit faster. The timestamps look identical, but I'll go with the ordering. So let's go 0.05 for level significance. So we're right in the middle for balancing type 1 error with type 2 error. In my opinion, I would feel like type 1 error is a little bit more dangerous with this. In these kinds of sciences, psychological sciences, if we reject this null hypothesis, there's a 5% chance of that happening. And if I make this bigger to lower type 2 error, I have a 10% chance of negating this. And sometimes that can be easily done in the psychological sciences. Sometimes these studies are done repeatedly, and only the ones that get published are the ones where it did go below alpha at 0.05. So I would say this is probably about the minimum I want to go for a study like this one, or excuse me, a maximum. Sorry about that, Zachary. We'll get you on the next one. So with at 0.05, next we have to check how the conditions are going to go. And I think we just have barely enough time to take a look at those. I should put that right there. But notice I'm clicking on those a lot. I appreciate the engagement. So one thing I want to take a look at before we take a look at these conditions are the way we did conditions here is very, very different. If you're doing the paired one sample t-test, then the conditions didn't have anything to do with one column or the other. We had to form the differences, and we did the difference in the beta endorphin levels. Conditions failed on this right here immediately. That looked pretty bad. But for this, when we check conditions here, we must show the distribution for both samples. So this again takes us right back to chapter 1, where we'll output a couple histograms, see how they look, and check with the robustness conditions to see if we're okay for the 2-sample procedure. Any questions at all, folks, before we go to that next phase? Okay, so let's take our RStudio. This one we'll need to maximize. It's maybe not maximize it, forget how much space that takes up. Let's see if we can get it going like that. There we go. First thing we need to do is import data. So that's going to be from text base. We're in chapter 18, and this is the one data frame we have, example 4. Everything looks normal, or everything looks ordinary here. So that's the right to import here at this step. Take a look at it. We've got 20 observations on 2 variables. So that's what we were expecting. Now we can start pulling the data out of here. I'll go with normal gets example 4 and select with a $sign normal children. Then skits example 4 $sign select and just go right down to schizophrenic. Now we have them both, and we'll give a histogram for both. Hist for normal, hist for skits. And let's just run it right now. This is not going to be our end answer to this, but we're getting started. If we run what we have so far, here's one downside of what we've done. You get one histogram at a time, and there's nothing terribly wrong with that. You can do one screenshot at a time to make all this work out for us. You can use the left arrow to go to the prior one and the right arrow to go to the next one. If you want to make it slightly more fancy, you can add this syntax right here. Now, I have to be completely upfront with you. I don't know exactly what the syntax is doing. I just know what the outcome is when it does it. We do PAR. I think that stands for graphical parameters. Possibly I should read that at some point. Then MF row, modify something probably, equals C. We're going to combine and do a display with one row, two columns. So if you put that in the middle, then just rerun everything, you get some fancier histograms, but it's completely optional. I'd say use that syntax if you like it. Next thing we have to add here is, once I can get these windows in a bare spot, we need a better description of what this is. This isn't normal children. This is a TAT score. It's just a point value. So we should go over here and say normal. XLab for the X label. We'll need quotes and then TAT score for ordinary children. Then same deal on this one, XLab equals TAT score for schizophrenic children. And let's hope this works out. Well, it's sort of there. Get a better view, click on the export, copy to clipboard. Then from here, I usually click on copy plot, but this version of RStudio doesn't want to work. I'll just take a screenshot at this stage. So here's where we are so far. We have about 3 minutes and some change to analyze this and decide if the conditions are met. So that's probably a good stopping point for us at this stage. The one thing to note is they're both skewed to the right. That's actually not terrible for that type of skew. Looks like a potential outlier here and a potential even more serious outlier on this one, but not terrible at the moment. If it was further to the right, we're looking at an overly influential outlier. And other thing to mention is, if this was our data, if it was a one sample test and we just didn't have that data, this is bad for a sample size of 20. We may not meet the conditions with this skew and the potential outlier. But because it's two samples, our combined sample sizes are N1 plus N2, 20 plus 20 equals 40. We actually have a great deal of robustness. We have 40 individual pieces of data. This is not looking as bad as it appears on face value. But we'll take a careful look at that when we come back on Wednesday to finish off this problem here. Well, any last questions, folks, on running through the robustness, well, up to this stage? Okay, I think this ought to be a good stopping point for us then. When we come back, we'll finish this one off and then move into chapter 19. Chapter 19 is now looking at categorical data. So to prepare for chapter 19, you might want to take a look at, let's get us there, chapter 15 once again, or let me make sure, chapter 13 once again. In chapter 13, we skipped this section because we just had no cause to use any of that information until we hit chapter 19. So I felt it's a good one to leave off. What I'm going to do is not go back into chapter 13 specifically. I'm going to take that information and just put it onto the chapter 19 notes. So that way the notes seem to flow better. But if you want to do the reading, you could go back to this section of chapter 13 to take a look at what it looks like in the textbook itself. Well, any last questions or comments at the moment, folks? Okay, well, have a great night. I'll see you all in Wednesday's class. And it's just 5 more weeks to go. We're just about there, everyone. Congratulations. Thanks, folks.